Hello from Athens. My name is Dr. Elena Kapogianni. I am an adjunct lecturer and researcher at the National Technical University of Athens. Welcome to the presentation entitled The Geotechnical Structures in the Ancient World, the Case of the Ziggurat of Worid in Mesopotamia. I would like to start this presentation by posing a question. What are the early signs of civilization? The cultural anthropologist Margaret Mead stated that the first sign of civilization in an ancient culture was a leg bone that had been broken and then healed. Such healings were never found in the remains of savage and competitive societies. In the animal kingdom, if you break a leg, you die. The healed leg showed that someone must have cared for the injured person, hunted on his behalf, and brought him food. Another early sign of civilization is the effort that had been made by ancient societies to mitigate the consequences of natural hazards. Natural hazards and disasters have been a fact of human life since the beginning of mankind. Disasters cause civilizations to collapse, but in some cases they have spawned innovation and led to more resilient societies. Natural hazards are naturally occurring physical phenomena that have a negative effect on humans and the environment, including the man-made environment. In some cases, they may escalate into natural disasters. They can be classified into two broad categories: A. Geophysical hydrological, such as earthquakes, landslides, tsunamis and rockfalls, and B. Climatological meteorological, such as extreme temperatures, droughts, and wildfires. Furthermore, certain geographical regions are characterized by moderate or high seismicity, leading to earthquake-related geological hazards, such as soil liquefaction, fault rupture at the ground surface, and earthquake-triggered landslides. As aforementioned, natural hazards and disasters have always accompanied human history. In around 1600 BC, the volcano of Santorini, Thera, erupted with such force that caused the collapse of the Minoan civilization. In 464 BC, an earthquake struck Sparta, killing more than 20,000 Spartans, leading to internal and external uprisings. In 373 BC, the ancient Greek city Eliki, the flourishing capital of the Achaean League, was destroyed during a winter night, probably due to a rapid and catastrophic landslide and due to a massive tsunami. The dramatic destruction of Heliki was widely discussed by many Greek and Roman authors and may have inspired Plato to contrive the myth of Atlantis. In Europe, a well-known case of an extreme natural disaster was the Great Lisbon earthquake in 1755. Approximately 60,000 people died due to an 8.5 magnitude earthquake and the subsequent seismic activity. Hazard and disaster mitigation and rehabilitation is a very important topic in engineering and in geotechnical engineering in particular. This has been made clear since the very early years of humanity. Initial efforts of humans to understand the basic principles of geotechnical engineering date back to the prehistoric ages. The attempt to control natural phenomena and hazards with the use of soil as a construction material has probably taken place well before the historical records. For example, retaining and fortification walls were often built during the antiquity. Stabilization efforts were made with the development of a systematic approach. Foundation engineering techniques were also well known, aiming to control the water content in the soil and to distribute the loadings of the constructions uniformly. A well-documented example consists the fortification walls of Troy, which was built during the Bronze Age. The Great Walls of Troy were constructed using large hewn stones attached together, including also a layer of soil between the foundation and the bedrock. The Great Walls of Troy are considered to be quite anti-seismic since the earth field of the sub-foundation acted like a seismic absorber. Another example of an ancient geotechnical structure is the polygonal wall in Delphi, in Greece, where the sanctuary of Pythia was located. The walls were built from stones with curved joints that had excellent adaptation between them. The Acropolis of Athens also includes extensive geotechnical works. Among the standing monuments of the hill, the Parthenon, the Erechtheion, the Propylaea and the Ariforion, the circuit wall serves a pure geotechnical purpose since it functions as a typical gravity wall, retaining the backfill that forms the plateau of the Acropolis. Soil stabilization with soil reinforcement materials is another geotechnical engineering technique used during the antiquity. The Great Wall of China includes parts which were formed as reinforced soil. More specifically, layers of earth and gravel were reinforced with layers of desert branches. Furthermore, the ziggurats, which were built by the Sumerians, the Babylonians and the Assyrians in ancient Mesopotamia, also included earth-reinforced techniques. These constructions consisted of walls covered with clay bricks and layers of mats, which were made on baskets and placed in the mud between the bricks as horizontal reinforcement. Additional reinforcement was included in some of the ziggurats in the form of ropes. The famous Ziggurat of Ur, the Great Ziggurat, was a Neo-Sumerian and built in the early Bronze Age. It was constructed in 3 layers and a temple was built at the top layer. The lower layer of the ziggurat was built in a height of about 15 meters, the middle layer with a height of about 6 meters, and the top layer with a height of about 3 meters. Various scientific methods and techniques can be utilized in order to investigate the behavior and the structural response of structures and monuments of cultural heritage sites. For example, smart instrumental monitoring and remote sensing can provide real-time information of both the natural hazards and the corresponding vulnerability in terms of structural response and distress, leading to a dynamic, time-dependent structural risk assessment. Furthermore, advanced numerical modeling can predict the expected response and distress of the structures and monuments under investigation when they are subjected to the anticipated hazards and structural loadings. Advanced numerical modeling is essential for the vulnerability assessment. For the purposes of the current study, numerical simulations of the Great Ziggurat of Ur has been performed by utilizing 2-dimensional 3-step numerical models. The mechanical and geometrical characteristics of the numerical models are similar to those of the original construction. The temple that existed at the top of the highest step was replaced with a uniform loading equal to 100 kN per meter. Non-cohesive sand was used for the soil material with a friction angle equal to 35 degrees, and inclined walls were included at the exterior surface of every step following the original inclinations. 2 different numerical methods have been used, and more specifically, the Bishop method for slope stability analysis and the finite element stress analysis method. Numerical models were examined initially without additional reinforcement, and the maximum shear strains were calculated, as well as the failure mechanisms, the strain vectors, and the safety factors. Furthermore, numerical models, including soil reinforcement at the left side of the model, were analyzed. Significant smaller deformations were calculated at the left side of the models, which included the soil reinforcement as expected. In conclusion, ancient civilizations had awareness of advanced construction techniques and applied reliable methods to deal with structural loadings and various natural hazards. The remains of such structures can be found today at different archaeological sites worldwide. Earth-retaining techniques used for the construction of the massive pyramid-like structures, ziggurats, were examined, and more specifically, the contribution of soil reinforcement to the structural safety. The analysis showed that soil reinforcement plays an important role to the structural safety, increasing significantly the safety factors, decreasing in parallel the strains and the deformations. The numerical models utilizing the finite element stress analysis method are in good coherence with the Bishop analysis models. It is evident that it would be rather difficult to build the ziggurats at the specific heights and with such steep inclination without the reinforcement materials. And some comments for potential further research. Cultural heritage sites include sensitive engineering structures and monuments, not only temples and buildings, but also masonry retaining walls with limitless lifetime and rather limited intervention options. They comprise fundamental elements of the national and international heritage and they feature an elevated risk level. Their overall risk is very high for two reasons. First, a serious damage and especially a total failure may be irreversible and thus unacceptable, and secondly, a failure may lead to injuries or even fatalities. The assessment of the structural risks of structures and monuments of cultural heritage sites can be achieved through the quantitative assessment and management of the main natural hazards and loadings and the vulnerability of the structures and monuments. The combination of scientific methods, such as advanced numerical computational modeling with structural monitoring, can assist in this regard. Concerning real-time structural monitoring and remote sensing, I would like to encourage you to take a look at the other paper that is included at the conference proceedings and is entitled Quantification of the Structural Response of Historical Construction, Investigation of the Strain Variation at the Acropolis Circuit Wall. Thank you very much for your attention.